Alright guys, we're going to practice the review problems that I posted to prepare for the Unit 9 exam. I am going to skip some of them just because there's not enough time in one video, and I'm going to move pretty quickly. So hopefully you've already tried them, and I would encourage you, if you haven't yet, to pause the video before I do each problem and try to do it on your own. So number 11, we've got an integral from 1 to 2 of 8x cubed plus 3x squared dx. This is going to be a simple one because it's just a power rule situation. So the antiderivative of 8x cubed is going to be 2x to the fourth, because I've got to go up 1 degree, and I've got to make sure that I leave this so that when the 4 does come down to take the derivative of this, I'm left with an 8. Okay, plus, and this is just going to be x cubed. And since that is the antiderivative, I now am going to use the fundamental theorem of calculus to evaluate that by taking the difference between this antiderivative evaluated at 2 and the antiderivative evaluated at 1. And I'm going to evaluate those. I should get 40 minus 3, which is 37. All right, on to number 15. The first thing I'm going to do here is rewrite this. I'm going to turn this into sort of like a polynomial, and I'm going to separate this into two fractions so that I've got my square root of u over u minus my 2u squared over u, okay? And when I rewrite it like this, it makes it easy to see that I can just subtract my exponents in each of these fractions. So I'm going to have the integral from 1 to 9 of u to the negative 1/2 minus 2u. And I'm taking the derivative of this whole thing, or the antiderivative of this whole thing with respect to u. That's going to be the next move here. All right, so again, it's just a reverse power rule, essentially. So I'm going to have a u to the positive 1/2. I need this to be a 2 and minus u squared. And I'm all right there. So now I can subtract this function evaluated at 9 minus this function evaluated at 1. Okay, so this ends up being negative 75 minus 1, which is negative 76. Example number 17. Notice the variables aren't always x, right? Just because it doesn't say dx and the function isn't of x doesn't mean we change the way we do this, since these variables are the same as the variable that we're indicating we're taking the antiderivative with respect to. We don't have to do anything differently. We could replace all these with x's and just treat it like that if we want to. So this is a situation where I've got a composition going on here. I have a function within another function, and that's being multiplied by another function. So I'm going to want to make a U-substitution here. I'm going to say let u equal y squared plus 1, and if that's the case, then du is going to equal 2y dx. Or dy, rather. Okay, so now I'll be able to make a substitution for all of the components that I needed to make a substitution for here, and I'm just going to check and make sure that I have those components. So I've got my y squared plus 1, that's equal to u, and I've got a dy, that's good, and I've got a y, that's taken care of. There is no 2 in here. So I don't want this 2 to be represented on this side of my equation. So I'm going to rewrite this as 1/2 du is equal to y dy. And now I can make a direct substitution there. So when I rewrite this with my u substitutions, I do have an integral, but I'm going to have to change the bounds of that integral because I'm working with u functions now. So if u equals y squared plus 1, then what happens when y is equal to 0, like we have here? Well, if y is equal to 0, then u is going to be equal to 1. Okay, so that's a new lower boundary for this integral. And what happens if y is 1? Well, then we have a 1 squared plus 1, which is 2. So our bounds of integration have changed here. And I can rewrite it by making my substitutions. Instead of y squared plus 1, I'm using u, but it's raised to the 5th power. And instead of y and dy, I'm replacing that with a 1/2 du. And so now I can use my reverse power rule here. 1/2 times I have u to the 6th, but it's a 1/2 u to the 6th, evaluated from 1 to 2. So that's going to be equal to whatever I get when I plug these in. So this is going to be equivalent to 64/12 minus 1/12, which is 63/12. 21 is another situation where I'll need to use a U-substitution because I've got a composition, and that composition is cosine of another function, so I'm going to let u equal v cubed. And if that's the case, then du is equal to 3v squared dv. So let's make sure that these are all components I need. Do I need the dv? Yes, I do. Do I need the v squared? Yes, I do. That's going to be really helpful. But the 3 is not going to be something we're going to need. So I'm going to reuse or repurpose that 3, send it to the other side. V squared dv. All right, now I've got something I can use in a substitution. So I'm going to rewrite this as the integral of cosine of u du. Say 1/3. Let me deal with the bounds of integration here. What should I do about those? Well, if v is equal to 0, well, u is equal to u0 cubed then, so it's still 0. And what if v is equal to 1? Well, u would be equal to 1 cubed, which would be 1. So our bounds haven't changed, but we did still have to consider that. And now I'm taking the antiderivative of cosine of u. So this is going to be the same as 1/3 times the antiderivative of cosine, which is sine, from 0 to 1. All right, so I can plug those in now. And sine of 1 is not a nice number. This is not something that's going to be easy to deal with, but we do know that sine of 0 is 0, and 1/3 times 0 is 0. So in the end, our final answer is just 1/3 sine of 1. 27 is another good example of where we would use a u substitution. In this case, I would let u equal x squared plus 4x. And in that case, du would be equal to 2x plus 4. And I'm just going to check and make sure that these are all things that I need. Oh, and I should have my dx. I do need that dx. This does not quite look like something that I want. I want an x plus 2. So I'm going to see if I can rework this so that there's an x plus 2 there. And there's a pretty simple way to produce an x plus 2. If I factor out a 2, I'm left with x plus 2, and that uncovers this other component that I needed, but I don't need that 2. So I'm going to rewrite this as 1/2 du is equal to x plus 2 dx. So now I have all of the components that I'm looking for here, and I can rewrite this indefinite integral as 1/2, that's the constant that I'm going to pull out of there, and then 1 over the square root of u du. And so now I need to take the antiderivative here. When I take the antiderivative, I'm going to have 1/2 times, this is going to be 2 radical u. And remember that you want to think of this as a u to the negative 1/2. So you want to consider how you could reverse power rule, use the reverse power rule there to get the antiderivative. I am going to say plus c because this is an indefinite integral, so I don't necessarily know what my bounds of integration are. I'm not going to be canceling anything here. And now I'm going to imagine that that 1/2 has been distributed to both terms inside the parentheses. So the square root of u plus c times 1/2, which is just c, because we didn't know what c was in the first place. The last thing I'm going to do is make sure that I replace my substituted value for u back into the function. So the square root of x squared plus 4x plus c, and that is my final answer. I'm just going to do one more from those practice problems. It's the last one, number 38. I'm going to want to use a u substitution here again. The composition that I'm going to focus on is this one here. The reason that I'm choosing that is because if I choose this composition, where I let u be equal to secant of t, I need to think about what the derivative of that is going to be and if that's going to be useful to me. Whereas if I let u be equal to 1 plus tangent of t, you're going to see that something pretty nice is going to happen that's going to help me deal with these other components. So I'm going to do that. Let u equal 1 plus tangent of t. And if that's the case, then du is equal to the derivative of 1 plus tangent, which happens to be secant squared of t dt. And that's why this is helpful, because the derivative of this interior function is this function. Whereas if we had used secant of t to be our u, we wouldn't have gotten a derivative that would help us deal with this. Okay, let's make sure that all of these are components that we want. Secant squared of t is there, and dt is there. This is good. We've got everything we need. Okay, so I'm going to rewrite this then as a definite integral of u to the third du, and I just want to be careful about the bounds of integration here. So let's say that t is equal to 0. What's that going to do to u? Well, u is equal to 1 plus tangent of t. So tangent of 0 plus 1, that's going to be equal to 1. So we're now going from 1 to, what if t is equal to pi over 4? Well, u is equal to 1 plus tangent of pi over 4. Tangent of pi over 4 is 1, so we have 1 plus 1, which is 2. So this works out pretty nicely here. Okay, let's take the antiderivative there. It's going to be a 1/4 u to the 4th, evaluated from 2 to 1, and now I can substitute those values. And this leaves me with 4, 2 to the 4th divided by 4 is 4, minus, and this is just a 1/4, so if I get a common denominator and subtract, that's 15/4.